This conference will now be recorded.
Is that good? It's working?
Yep.
Good.
I see it. Okay, so let's move on to the next slide. All right, an overview of today. We'll be talking about neural networks, basically introducing the very basics of neural networks. And we will go through that in a little bit more detail just to make sure that everybody has the basics. I apologize to those of you who are already using neural networks for whom this might be trivial, but I just want to make sure everybody's on board. And then we move over to permutation importance test, which is a general machine learning interpretation technique that applies for neural networks, but also other machine learning. And then we do saliency maps, which are more just for neural networks. And the last two topics there will be covered by Ryan. Okay, next slide, please. All right, just to give you the big picture first. So let's say you have a sample application where you have some kind of an input X, and your task is you want your machine learning method to predict some output Y. So on the top left, you see in this case, the input X is an image, but it doesn't have to be an image. It can be image type data, it can be a vector, it can be a mixture of scalars, it can be a mixture of all of the above. So you can throw in pretty much whatever you want. But just for the visualization here, just for explaining it, we assume the input is a single image type. And you feed that into your machine learning method, and then as output comes an estimate of Y, but you're assuming that you also have the exact results for that, so the correct answer, what it should be. And it can be anything you want. So again, it can be an image, it can be scalars, it can be a mixture of that. But again, for simplicity, we'll just deal with Y being a scalar for today. Next slide, please. Okay, so step one, let's try a very, very simple machine learning method, good old linear regression. So what you see here on the left, you have your image, and then you see what we call the input layer, which are these yellow blobs over there. And each pixel basically is represented by one yellow circle. And this is really, there's nothing big happening. There's nothing big happening. You just see that the input layer really just holds the values from your input samples in kind of a vector form. So you kind of vectorized your image here. And then you apply linear regression, which means that you're saying my output is some constant b plus some weight w1 times x1 plus w2 times x2 plus w3 times x3, etc. Okay. And that's a machine learning method and gives you a result, but in most cases, linear regression is way too limited because it's, surprise, linear. So you would not expect this to give good results for most applications. So let's try something more complex. Next slide, please. Okay, now we have several different layers of linear regression. So we just have a concatenation of linear regression after linear regression after linear regression. So we're starting again on the left-hand side with all the yellow circles, which just hold the input data. And then the first blue layer to the right of that is connected just like before through linear regression. So each one of those blue nodes has is basically calculated linear regression from the previous layer. And then you could repeat that whole thing and you do that again and again. So each layer is calculated linear regression from the previous one until you get to the output. And so many of you would ask probably, why would we do this? Because what do we get? Next slide, please. It turns out what I've just done is makes the problem more complicated without gaining anything. Because if you concatenate linear transformations, you still get a linear transformation. So our output is still just a linear regression of the input. So how can we achieve nonlinear functionality? Next slide, please. So the whole trick over here is to sneak in some nonlinearity between any two layers. So imagine our first blue layers to the leftmost blue layer there is still just obtained with linear regression. But then I sneak in a tiny little nonlinearity from the blue to the green node, and that's just a scalar function, and I will show you some examples in a moment. And so between any two blue layers now, we have this green layer in between that introduces some nonlinearity. Okay, next slide, please. And just to show that more visually, you see always the blue blocks are always just linear regression. And then you have these greenish blocks, which just one by one apply a scalar function, for example, the one on the bottom left or bottom right, to the output value there. And then that's being fed into the next blue layer, which then uses, again, linear regression based on the green nodes. So you're not taking immediately the blue nodes, you're taking the green ones now as input for the linear regression for the next layer. And you repeat that over and over. So this is really, we had linear regression followed by linear regression followed by linear regression. And now we're just sneaking in this little simple nonlinear mapping. And it can be as simple as on the bottom left. This is a very, very common activation function. It's what we call this. This is called Relu for rectified linear unit. But all it does is it takes an input value x and it cuts it to 0 whenever it's negative. So it's just 0 as long as x is negative, and then it's x when it's positive. On the bottom right, there's another one, and Ryan will actually talk later more about different types of activation functions. But just know that this f of x is now just one of those functions below or something similar. It's really just a scalar function that introduces some nonlinearity. Next slide, please. So what you're seeing now, and I'm just merging this blue and green stuff pretty much together. And in fact, from now on, I won't even show the green stuff anymore. From now on, we will just assume that the blue nodes are obtained by linear regression plus my nonlinear activation function. And so we call this one unit, one neuron, and we'll look at that in more detail in a second. But again, each one of those nodes is now just linear regression plus my nonlinear activation function. And what you see here is already a basic artificial neural network. We call this a fully connected network because it consists of all fully connected layers. And so you already have now the overall idea of a neural network. It's just a combination of regression and nonlinear mapping repeated many times over and over. The surprising thing is, as simple as this is, this can act as kind of a universal function generator. And there's actually a theorem in computer science that's called the universal approximation theorem that says that with this kind of architecture, you can approximate, if you have enough neurons, you can approximate pretty much any function, I think that's continuously integrable or something like that, you can approximate as closely as you want to. What it doesn't tell you is how to choose the weight such that that happens. And in fact, as you will see later, there's no way of finding those optimal weights usually. There's just, finding a good enough solution to this. So we know an optimal solution exists, but we don't necessarily know how to find the very best solution, but we kind of know how to find good solutions. Okay, next slide, please. You've probably heard the term deep learning very often, and deep learning really just refers to neural networks that have many of those hidden layers. So let's just look at these hidden layers again. So the input layer, the yellow things, again, they have no real functionality. I mean, they only hold the input values. So the input layer just holds the input sample data. Then the blue nodes are called hidden because it's kind of hard to figure out what each node means once this network has been trained. With the yellow nodes at the input, you know exactly what they mean because it's your input data. Likewise, the very right side, the red node, you also know exactly what it means because it's supposed to estimate your output data. The blue ones in between that are kind of implicitly learned, you don't really know what each node means. There are visualization techniques that can help you figure it out a little bit, but overall, it's really hard to figure out the meaning of those. And so we call those hidden layers because they're not so easily visible from the outside. So what you see here in the graphic is an example of shadow learning because you only have about 3 layers. And if you have you have exactly 3 hidden layers. And if you only have a few layers, you call it shallow. And early on in the 1980s, those already existed. And you couldn't, at that time, the techniques weren't there to really have very many layers and train them. So you could only train shallow neural networks. And that's why pretty quickly there was a big hype and everybody was saying, oh, they're going to do everything that humans can do, but they were actually pretty stupid. So pretty quickly, the term artificial intelligence in the 1980s became artificial stupidity because they really couldn't do much. Then about 10 years ago came the big breakthrough where we figured out, and 2 research groups actually figured out independently, what kind of techniques and tricks you can use such that you can really train very deep layers. So now we're able to have very many layers. I usually try to use as few as possible, but there are applications where you have 100 layers. So, and that's clearly deep learning. Where the cutoff is kind of debatable. Some people, if they want to use the word deep learning and they only have 3 layers, they may still call it deep learning. There is no exact definition of what is shallow learning and what is deep learning. So you can kind of use the word as you want to, but generally deep learning means that you have at least more than 5 layers. But again, it's a question of debate. But the key thing is that ever since we were able to train this many layers, we can actually, artificial intelligence has been taken off. We can do very impressive things with that. Next slide, please. So let's look at a single unit again. So a single unit, also known as a perceptron, and Ryan, you have the old version of the slides, I think.
I have V2. Am I supposed to have a different version?
Yeah, final is supposed to be at the end.
Oh, I thought final came earlier. Okay.
Okay.
Yeah,
let's go to that because the later slides are going to be really different. So.
Okay.
Any questions so far? While it's loading the other file.
Hi, Emma. This is John. I do have John Crockett. I have a question, and that is you have mentioned that these hidden nodes can be difficult to interpret. Given that they're considered difficult to interpret, should much time be spent trying to interpret them?
That really depends on the application, but my take is, I've tried a large number of different visualization tools, and so has Ryan. And I think we would both agree that usually this trying to figure out for each node itself what it means is fairly futile in our applications. It's a little, if you're trying to distinguish between cats and dogs and you can figure out, oh, this neuron represents ears and this one represents eyes, that's great. But we usually have objects with very fuzzy boundaries. We don't have these pretty features that stand out separately. And so for us, it's much harder to really figure out what the different neurons mean. And even with cats and dogs, it's not easy. So what we have found useful though, both Ryan and I, is to try to interpret the entire network and figure out where, for example, where was the neural network looking. But in fact, we'll see an example later in today's presentation because Ryan is actually going to talk about saliency maps, which is the kind of approach, heat maps, which I strongly recommend rather than looking at the individual neurons, because at least I haven't found anything useful when I've been doing that. Very little useful information.
Thank you.
Okay. So here we have just a single perceptron. So what we would see before is a blue node with a few errors coming in and some coming out. And of course, what's coming in, these are all different signals. What's coming out of the blue node, even if you have several layers, it's all the same. It's all white that's coming out. And so just again, you have these inputs over here on the left, and they're multiplied by weights. You add a bias, and then you have the activation function f of x, and out comes y. Next slide, please. And the main key point here is, again, to remind you what is actually being learned and what changes with samples. So everything you see in red over here are the weights and the bias. And those are the ones that the neural network is learning while it's being trained. So those are the things that are being adjusted while you're training the neural network. Everything you see in blue just depends on the sample. So the xi's are just what's, you feed in your sample the input, you feed it through your network, and that will result in those blue things. And the other thing I wanted to point out is you can now describe y as a function of the sum of wi xi plus b. So this tells you basically the input-output relationship between what's coming into your perceptron and what's coming out. Next slide, please. So now just backing off a little, people often ask, where does this actually come from, this whole idea of setting neural networks up this way? It really comes from the human brain. So when you look on the left side, it was actually suggested back in the 1950s and 1960s. The idea was the human brain consists of all of this many, many neurons, each of which is relatively simple, and they're connected to each other and they pass signals around. And in fact, the way humans learn is also by having these connections between neurons that can grow in size and thus can let more or less signal through. And that's very equivalent to the W's that are the connection strengths in the neural networks that you see on the right side. The big difference, I think, in the models is, the summation is almost similar because you're really feeding electrical signals that kind of add up in the brain. So that's similar. What's very different is the activation function. So the activation function you use in artificial neural networks on the right is very different from what's happening in the human brain, which is more like a saturation thing. And then the other thing that's different is that you don't have as much directionality in the human brain. Because, our neural network is arranged in these nice orderly layers, and it goes from left to right. And in the human brain, it can go back and forth. But actually, things like the visual cortex, for example, are surprisingly similar to convolutional neural networks. So although there is a lot of simplification going from the human brain to the artificial neuron, the systems you're getting out of it are actually surprisingly similar in capability, and they use neural networks more and more to explain human behavior in cognitive science. All right, moving on to the next slide, please. So now you know what a fully connected neural network is. You know the input nodes, the yellow ones that are just a placeholder, the hidden nodes, which consist of your standard perceptrons, and then your output node, which often uses regression and often has no activation function or may have a different one. So they usually play a slightly different role. Next slide, please. Hold on. And two things I wanted to mention, going back. Because each one is called a perceptron, these fully connected neural networks are often also called MLP or multi-layer perceptron network. But usually you call them fully connected neural network or dense neural network or consisting of dense layers. And again, here, each neuron in one layer is connected to all neurons in the previous layer, but nothing else. So it's really, this one is sequential. So you have layer by layer by layer. All right, next slide, please. So again, what is fixed and what is learned, just like you saw with a single perceptron before, the weights and the biases for all the hidden and the output neurons are learned. And that's what we call training. They're also what we call hyperparameters, which are things that are typically chosen and fixed ahead of time by the developer before you train it. But you can also determine it by parameter search, which is computationally expensive, but Ryan is going to cover that a little later too. So the hyperparameters, what are they? They are like things in the architecture, such as the number of layers, the number of nodes per layer, the type of layer, because we've only covered fully connected layers, but there are also other ones, and things like activation functions. And those are all things that you have to choose before you can train your neural network. Next slide, please. So just a quick interactive thing. I'm showing you this very simple neural network that has 1,000 input nodes, 50 and 20 nodes for the hidden layers, and one node at the end. We want to figure out how many parameters do we need to learn this network. So let's think about biases first. How many biases are there for each node? You can type it in the chat, you can unmute yourself, but I would love to hear an answer. How many biases per node? Okay, somebody already types in 50 plus 20. Yes, you have, okay. So you have one bias per each blue or red node. So John is almost right, because they have 50 plus 20 plus 1, because the input layer actually doesn't have biases. The hidden layers do, and the output layer does. And since we have 50 plus 20 plus 1 nodes in the hidden and output layer, we have 71. How about the weights? And I think that goes more where John Crockett was going, because now we have to take into account the input layers. How many weights do we have? How many weights do we have just between the yellow layer and the first hidden layer? Any idea? Okay, I see 1,000 plus 1 times 50. I see 1,000 times 50. Okay, I'm going to go with 1,000 times 50 for just the first layer, because each of the 50 nodes in the first hidden layer has 1,000 arrows coming in, and each arrow has one weight. So for the very first one, it's already 1,000 times 50. Oh, okay, and Dave is saying, okay, he treats the bias as a node. So then, yeah, okay. So then it would be 1,000 plus 1 times 50. We're going to go with 1,000 times 50 here because we treated the biases and weights separately. So Ryan, if you could go to the next slide. Okay, we already went. So for the number of weights, it's the sum over each hidden and output node, and for each one of them, the number of incoming links. And if we go to the next slide, we will see then that the number of biases is 50 plus 20 plus 1. The number of weights is 50 nodes times 1,000 links plus 20 times 50 plus 1 times 20 for the entire thing. So it's 51,020 weights, which means the total number of parameters is 51,091, which is huge, right? This is a lot of parameters. And if you think you're dealing with an image, you could easily have 1,000 pixels. You could have a lot more than that. So let's go to the next slide. So that's one of the drawbacks of the fully connected networks. And I'm just giving you a tiny little preview of convolutional neural networks, which we're going to cover next week. But I'm giving you a preview because they will be mentioned in Ryan's slide later on a few times. And I just wanted you to have just a tiny little bit of an idea of what's coming there. So our fully connected network, unless there are very few input layers, have lots of parameters, as you just saw. And if you want to train that many parameters, not only is it computationally expensive, you also have to have a lot of training data, right? And we usually don't have that much labeled training data. So it's usually not very efficient for processing images and stuff like that. So what can be done? So the idea behind using convolutional networks is that you utilize the spatial structure of things like images. Like which pixel is a neighbor of which other pixel, because really you maybe to find a local pattern, you don't have to connect one node to all of the nodes in the previous one, but maybe just some neighborhood nodes. And so you utilize the spatial structure, and it builds then on concepts of mass and traditional image processing, like you used to, like Sobel operators and stuff like that, as you will see. And what you get then is a very sparse layer connectivity. So each neuron in one layer only connects to few neurons in the previous or in the next layer. And that cuts down drastically on the number of parameters to be trained, and it's also very good at finding patterns in images. So it's generally excellent if your input data are images. Next slide, please. So a few more things. So now let's say we have already made the choices for the architecture. Oh, there's a question. How does the vectorization of the original image array preserve neighboring pixel? Well, that's an excellent question. If you use a convolutional neural network, you don't vectorize, because you're exactly right, then you're losing your neighborhood information. So if you're doing a CNN, you would probably draw like more of an array in the beginning. So you would keep the image structure intact and not vectorize. Excellent question. Okay, in the interest of time, let me just go through the slide a little faster. The key point I want to make here is if you look at the image on the top right, you see that we already figured out what the formula is to go from one layer to the next. It's this formula in the first yellow box, y equals f activation of the linear regression stuff. If you were to concatenate that and write it all out, it would be very messy, but doable. And so you would get an entire function that says y network output, so your y at the very right, your red node, is a function of the inputs, the weights, and the biases. And the only thing that changes with different samples are the output and the inputs. All right, next slide, please. So, okay. So in the previous slide, you saw how easy it is to go forward and that you can express it in a single function that's closed form. And you could also see how fast it is, because you just have to evaluate all the linear regression activation. So that's super fast. Now we're going to ask, okay, how do we train the neural network? Because that's the part that's slow and that's hard to do. And the first thing we need to do for that is we need to find a way to tell our network what exactly it should be doing. You feed in the input and output, but what should it do with that? What constitutes good performance? And to do that, we define a loss function, just like we did, for example, in lesson number 2 for linear and logistic regression. So the cost function that's to be minimized by the neural network. Just a very simple example. If you give it n training samples with labels, so you have xi is your input data vector, or even if it's an image in this case, you vectorize it. Yi is the correct output, and we assume for simplicity today it's a scalar, and yi tilde is the estimated output. Then you can just do again a mean square error over all the different samples. So if you have n different samples, you just get this L function here, 1 over n sum of the differences squared. So do you remember regularization was induced for linear regression in lesson 2 to reduce overfitting? And so you can do the very same thing also over here. I just want to show you this idea. So your loss function can also be the sum of several terms. For example, the first one could just measure precision, and the second one could be regularization that keeps the weights and biases small. So in this case, it's just one that keeps the weights small. And there are many, many other ways, and I actually encourage you to really think about how you choose your loss function, because how you perform good performance, how you measure good performance is crucial to getting good results. So we only showed you the very simplest ones here. We could easily spend an hour talking about loss functions, and again, it's something we can do in lesson 6, but for now, let's move on and just assume we have a loss function, like the simpler one over here, and let's go to the next slide. So now, remember how we made you go through in session 2, the whole process for linear regression? And there was a reason why we did that, because the whole thing can now generalize to neural networks. So we're using gradient descent to minimize the loss function. And here we're just reviewing in one slide what we did in lesson 2. We basically set up our loss function to be the MSE, which is pretty much the same as in the slide before. And then we substituted the formula that we had for linear regression for yi tilde or yi hat over here into that MSE equation. That's what you see on the top right. And then we took the derivative with respect to the weights. That gave us the term that's one line further down. And then we used that term to define our update rule, because now we're following gradient descent. So we're going in the direction that decreases our loss function the most by going one step along the negative gradient descent. And so that gives us our update rule. So again, all we did was we defined our loss function. We substituted the model in there, which was the linear regression model formula in this case, but would for the neural network be the big function that we had before, the big F. Then we take the gradient with respect to the parameters, and then we get the update rule. Next slide, please. So if you do the same for neural networks, for our example before, you first have your loss function up there at top, and then you substitute your Y network output function that we got before for the yi tilde in there. So you get this big, messy, closed form formula right there. And then, so that's step number 1 in the neural network training. Step number 2 is to take the derivatives then of that huge expression of L with respect to the weights and biases. And that yields then the update rule to minimize the loss function, just like we saw on the previous slide. And then we choose random values for weights and biases. And then we apply the update rule iteratively. So we do that over and over and over to change our weights and biases. So we're using gradient descent to minimize our loss function. And that uses a stopping criterion, either the number of epochs you want to have, we can discuss what epochs are later, or some other kind of criterion, and it just continues until it reaches the stop criterion. And then you're hoping that it returns you decent values for the weights and biases, and your neural network is trained. But the key question I have for you, based on everything I've told you, does this approach give you a global or local minimum for the loss function? Does anybody want to? Yeah, local, exactly. Because it's gradient descent. If it gets to local minimum, it gets stuck there. And there are techniques for getting it out of there, like, pushing it out a little, disturbing a little, and seeing what happens, things like that. But what people mostly do is that they start with different random values in step 3. So you run the whole thing several times with different random values as start weights and see which one gives the best minimum. And so you never know for sure whether you reach the global minimum. What you really only know is whether the performance of what you're getting is good enough for your purpose. But there's always a possibility that if you would have done another 1,000 runs, you would have gotten maybe something better. It goes in the direction of simulated annealing, yes. You can try to push it out of there. Same idea. Okay, next slide. Okay, I will turn it over to Ryan.
All right, so we're going to do a quick section on activation functions here, just to expand on what Imme said in section 2. So there's many different types of activation functions. The 2 that Imme showed were the Relu, which is the rectified linear unit, and also the tanh, the hyperbolic tangent. But there's a whole bunch of others. If you really dig into the topic deeply enough, there's a whole zoo of activation functions out there. So I just want to give people some general guidelines in choosing the proper activation function. So for the output layer, it really depends on what type of prediction task you have. That'll determine what activation function you want to choose. So if your prediction task is binary classification, you almost always want to have a sigmoid activation function at the end, because sigmoid pushes the output to range between 0 and 1 so that it can be interpreted as a probability. and you'll see that in some plots on the next slide as well. If you're doing multi-class classification where you have more than 2 classes, so let's say you have K classes, you're going to have K output, you're going to have K nodes in your output layer or K neurons in your output layer. And in this case, you want the outputs from all K of those neurons to range between 0 and 1, and you want the sum of the outputs to be 1, so that they can be interpreted as probabilities of, I'm going to trip over these words, mutually exclusive and collectively exhaustive classes, assuming that your classes are mutually exclusive and collectively exhaustive, which they should be if you're setting up a neural net to do multi-class classification. So yeah, in that case, you want to use the softmax activation function. If you're doing unbounded regression, where you have a value that can range from -infinity to +infinity, you probably don't want an activation function, or you can use a linear activation function. In some neural net libraries, you'll see that terminology where the activation function can be linear, but that's the same thing as having no activation function whatsoever, because kind of the definition of an activation function is that it's nonlinear. And then if you have bounded regression, for example, let's say you have an output that has to be non-negative, in that case, you can use Relu or the rectified linear unit. So for example, if you're predicting precipitation, you can't have negative precip. So there's no point in allowing negative values to be spat out of your neural network. So in that case, you could just use a Relu activation function. If you have a weirder, not necessarily a weirder, but just a different bound on your output variable, for example, say you have an output variable that has to be greater than 2 and less than 10, it's not super easy to set up an activation function that can achieve that. But what you can always do is normalize your output variable. So you can take the physical values and then normalize them to all lie between 0 and 1, and then you could use a sigmoid activation or a tangent or a Relu activation. And then once the neural network has made its predictions in normalized space, you can denormalize back to physical space. And then for the hidden layers, I really have no general guidelines here on what the best activation function is to use, except that I've had the most luck using Leaky Relu or the Leaky rectified linear unit in almost all my applications. People these days typically use Relu or a Leaky version of Relu for their hidden layer activation functions, but there's some other more exotic types of Relu that can be beneficial as well. So with that said, I'll go to the next slide, which shows you plots of 3 of the more standard activation functions. So these 3 have all been used for quite a while. They're pretty popular in the literature. So the green curve is showing you the sigmoid activation function. The x-axis is the input going into the activation functions. That's the value before you've applied the activation. And then the y value is showing you, the y-axis rather, is showing you the value after applying the activation function. So as you can see with the green curve for sigmoid, it forces everything to be in the range from 0 to 1. So it's good for binary classification when you have probabilities. Then there's the tanh or hyperbolic tangent activation function that forces everything to the range of -1 to +1. And then there's the Relu activation function, which Imme has already showed you, that just gets rid of negative values and sets them to 0, and then it doesn't touch positive values. This next slide is showing you 3 more exotic versions of Relu. So the purple curve is the Leaky Relu. And like I said, in my experience, the 2 activation functions that tend to work best for the hidden layers are just straight up Relu and then Leaky Relu. I found that Leaky Relu usually works a little better than straight up Relu. I've also tried the more exotic activation functions here, which are the LU and the CELU. So LU being exponential linear unit and CELU being scaled exponential linear unit. And in my experience, they haven't worked any better than Leaky Relu, but your mileage may vary, of course, depending on your problem and whatnot. Yeah, I'm not sure if there's much more I want to say about this. There's a motivation for having the fancier types of Relu, and I'm not going to get into the fully detailed explanation of it. But if someone is curious later, you can ask me, and I have a paragraph somewhere in one of my papers that explains it. So when you use straight up Relu, which completely gets rid of negative values and sets them to 0, often that leads to dead neurons inside your neural network. So there's certain neurons that persistently always have negative activations. So Relu persistently always sets those negative activations to 0. And that means when you do gradient descent, the weights at that neuron that's constantly producing 0 values never get updated. So often when you use straight up Relu, there's neurons inside your network that just die. And after a few epochs, they stop being updated, and they stop being updated for all time. And that often leads to bad predictions. So by making your Relu function a little bit leaky so that you're preserving the magnitude of these negative values somewhat, you can avoid the problem of dead neurons. So on the right-hand side here, I know this is kind of a complicated figure, but I'll walk you through it. So this is an example of using leaky Relu for a convolutional neural network. So in panel A here, you're seeing the input image, which is just a normalized radar image. I believe it's normalized reflectivity. So I've normalized everything to z-scores or to a Gaussian distribution. So it's zero-centered and the values are all almost nothing is less than -3 or greater than +3, which is why you see the tiny values in this image. And then panels B, C, and D are showing you what the filters or feature maps look like after running a convolutional filter. And then panels E, F, and G are showing you what those same feature maps look like after running the activation function. And in this case, the activation function is leaky Relu with a slope of 0.2. So it has the same shape as this leaky Relu curve, this purple curve that I plotted here. If I were using straight up or strict Relu, it would completely get rid of all the negative values and change them to 0. So if I were using strict Relu and you looked at the right-hand column here, which is panels E, F, and G, you would see no blue pixels whatsoever. All the blue pixels in B, C, and D would become completely white because they would become exactly 0 in panels E, F, and G. But what you'll notice is with leaky Relu instead of straight up Relu, the magnitude of the intensity of the blue pixels has been reduced as you go from the second column to the third column. So the blue pixels or the negative values are still there, but they've been diminished in magnitude. And here in a small number of words is a written explanation of the stuff I just said about dead neurons. So leaky Relu is a compromise between retaining sparsity in your neural network, which is a type of regularization, but without causing dead neurons at the same time. So the next section is on dropout regularization, which is another one of the many types of regularization that you can use inside a neural network. So Imme has already talked about L1 and L2 regularization, which is something we covered in more detail in lecture 2 when we were talking about linear and logistic regression. You can also apply L1 and L2 regularization to a neural network. And on top of that, you can do something called dropout regularization, which you achieve with dropout layers. So to my knowledge, dropout is used only in neural networks. You can use it for any type of neural networks. You can use it for a fully connected net, a convolutional net, a recurrent neural net, etc. The reason I say to my knowledge is the field is advancing so quickly. I'm sure someone's figured out a way to use dropout regularization for some other kind of machine learning model. So you can apply dropout to a fully connected or a convolutional layer. You're going to find out more about convolutional layers next week when we talk about CNNs. So in this case, just think about fully connected layers. So what dropout does is you choose the layers in the network you want to apply it to. Often you don't want to apply dropout to the very last layer, which is the output layer or the one that produces your predictions, because applying dropout to the last layer often causes the predictions to be nonsense and causes really bad performance. So often you'll apply dropout regularization to every fully connected layer except your last layer. So when you apply dropout to a given layer, it randomly omits D% of the weights when predicting each training example, where D is a hyperparameter. So the dropout rate can vary anywhere from 0% to 100%, but obviously 0% wouldn't be useful because there would be no dropout, and 100% wouldn't be useful either because then you would have a very trivial predictor. So usually 50% is a good place to start with the dropout rate. The benefit of dropout is that it forces weights inside the same layer to behave with some redundancy, because for any given training example, any weight may be dropped out. For example, if you have a dropout rate of 50%, each neuron for a given training example has a 1 in 2 chance of being dropped out so that its weight isn't even used to make the prediction. So this forces other neurons in the same layer to fill in for each other and to or to co-adapt in the jargon from the original paper. So it forces neurons in the same layer to have some redundancy in the way that they behave. Redundancy means simplicity, and simplicity means regularization. So this is a way of encouraging a simpler model. Another way to think about dropout regularization, Imme wrote this really helpful comment at the bottom, is that it generates an ensemble of neural nets. Because for every single training example, the neural net knows, quote unquote, that a bunch of the weights are going to be dropped out. So that means that different weights have to perform the same task. Or another way to think about it is every time you run a training example through the neural net, a different set of neurons are going to be used to predict that training example. So you end up with each set of neurons being sort of like its own neural net. So you're creating an ensemble with a bunch of different neural nets, even though they're inside the same architecture.
And one thing I wanted to add, in addition to thinking of it as an ensemble of neural networks, you can then also think about doing a little bit of uncertainty quantification. So there's a paper out there that says you can use Dropout for a little bit of uncertainty quantification.
Yep, and that's covered briefly on this slide as well. So another thing that I want to stress is dropout regularization is something you only do during training, typically, almost always. You don't want to apply dropout when you have your trained neural net and you're just applying your trained neural net to new data. So if you're applying it to the validation data or the testing data, or in the wild if you're in a forecast or operational setting, you generally want to stop using dropout at that point. But there is an exception, which is if you want to do uncertainty quantification. So using dropout to do uncertainty quantification isn't necessarily the best idea. It doesn't always give you a calibrated idea of uncertainty, but it gives you some idea of uncertainty. So the idea is when you have your trained model and you apply it to new data, you leave dropout on. So that means it's going to treat your validation example or testing example or whatever as a training example, and it's randomly going to drop out some of the weights in each layer. So you can do that many different times. So for example, you can take your new data point and you can run it through the neural net 1,000 times with dropout, and that's going to give you 1,000 different answers, and then that'll give you a probability distribution like I've shown here. This is from a CoLab notebook that we're not going to use for this course, but it was used for one of the AMS short courses on machine learning. So the prediction task was the same as in the CoLab notebooks we have. It was predicting the probability that a thunderstorm will achieve strong rotation. And you can see a histogram of the various probabilities. This was over 1,000 runs or 10,000 runs or something like that. The red line and the purple line are on top of each other. So the purple line is showing the median of all the predictions and also the deterministic prediction with no dropout. And then that black line is showing the mean of all the predictions. The next thing I want to talk about, which is another specialized type of layer that you can put inside neural networks, is called batch normalization. So batch normalization can be applied after the activation function. I think there still remains a little bit of debate over where you should do batch normalization, but I think a standard is emerging that you always do batch normalization after the activation function and not before the activation function. So you can use batch normalization after the activation function for any hidden layer. I wouldn't use batch normalization for the output layer unless you know absolutely for sure that your outputs or your target variable follows a normal distribution, because batch normalization generally forces things to a normal distribution or a Gaussian distribution, as I say here, which has a mean of 0 and standard deviation of 1. So the whole idea is that often the raw input variables to your neural net, which in our case are weather variables like temperature and reflectivity and U wind and V wind, what I've done in the CoLab notebooks and what's a fairly standard practice is normalizing all your predictor variables to a Gaussian distribution. But when you perform transformations inside the neural network, you're doing all these linear combinations, and then you're applying these nonlinear activation functions, and you're generally doing several of those in tandem. So it's linear transformation activation, et cetera. You typically, by doing that, you change the distribution of the input variables. So even if the input variable started out following a Gaussian distribution, after a couple layers, they're not going to follow a Gaussian distribution anymore. And I'm going to get a little bit hand wavy with this because I don't have the time to explain all the reasons why. But generally, if the data coming into a neural net layer follow a Gaussian distribution, that's a good thing. Gaussian distributions have nice properties, quote unquote, that allow a neural net to converge more quickly. So it's a desirable thing often to maintain a Gaussian distribution as you keep pushing data through the network. So the text on this slide is a bunch of stuff that I just said. Yes, so Gaussian distributions have nice properties, quote unquote, again, waving my hands a little bit, which lead to faster convergence and also mitigate the vanishing gradient problem. And those are details that I unfortunately don't have time to get into right now. But you can read more about this stuff in the original paper on batch normalization by two names that I dare not try to pronounce, but from 2015. And also my dissertation, which is the Lagerquist 2020 reference on the bottom, contains a shorter explanation in chapter 4. It's just a couple paragraphs explaining why batch normalization is a nice thing. So on the right-hand side here, I'm showing you an example of what batch normalization does. Again, this is inside a convolutional neural network, or a CNN. So this figure is analogous to the one that I showed you a few slides back, except I've just added a new column. So in this figure, you have panels A through G, excuse me. And in this figure, you have panels A through J. So A through G are the same thing. So there's this input image, which is a normalized radar reflectivity. And then the second column is showing what the feature maps look like after convolution. The third column is showing what the feature maps look like after applying a leaky Relu activation. And the fourth column at the right-hand side, which is panels H through J, is showing you what the feature maps look like after applying batch normalization. So you'll notice that after applying batch normalization, you have an equal distribution of red values and blue values, or positive values and negative values, because everything's been forced to a normal distribution, which is zero-centered. So I've forgotten how many sections I have, so excuse me while okay. I'm going to skip section 6, which is on hyperparameter tuning, because you've seen how to do a hyperparameter experiment already in the lecture on linear and logistic regression, and also the lecture on decision trees. So this is a lot of stuff that you've seen, and these figures and the code going with them is all in the notebook as well. So in the interest of time, I'm going to skip past section 6, and I've got, looks like, about 10 minutes to tell everyone about the permutation test and then saliency maps, which are interpretation methods. Okay. So the permutation test, I'll tell you quickly what it does, and then I'll show you some nice animations to hopefully give you a better idea of the mechanics of it. So the permutation test is a way to measure the importance of each predictor variable averaged over all the examples in a data set. So you're measuring the average importance of each predictor variable rather than doing things on a per example basis, which some other interpretation methods do, as you'll see. The permutation test is applied to a trained machine learning model, so it doesn't involve any retraining of the model, which means that it's generally fast unless you have a huge number of predictor variables, because the number of permutations you have to do is 1/2 times n minus 1, with m being your number of predictor variables. So in this case, in the Colab notebooks, we have 41 predictor variables, which means you have to do something like 1,050 different steps of the permutation test, which isn't crazy. But if you had 1,000 predictor variables, you'd be doing almost 500,000 steps of the permutation test, which would usually take a long time, even though you don't have to retrain the model. Another thing about the permutation test is that it's completely model agnostic, so it can be applied to any type of machine learning model. Absolutely anything you want, it doesn't matter. So the importance, quote unquote, of predictor x sub j is determined by how much the model's performance declines when x sub j is permuted. And when I say permutation, what I mean is randomly shuffling values of x sub j over all the examples so that they end up being assigned to the wrong examples. But every other predictor variable is still assigned to the correct examples. So if you do that, you shuffle all the values of x sub j, which could be maximum reflectivity inside the storm, for example. If you shuffle all the values and the performance of the model declines significantly, that means x sub j is an important predictor. Whereas if you shuffle the values and performance doesn't go down significantly, that means either x sub j is an unimportant predictor, or maybe it's too strongly correlated with the other predictors. So the other predictors are standing in for the one that you've just permuted, so you haven't affected the model much by just permuting one predictor variable. For example, if one of your predictors was composite reflectivity and the other was 2 times composite reflectivity, obviously those have a correlation of exactly 1. So you could permute either one of those predictor variables, and it shouldn't have a huge effect on the model because the other predictor variable still has all the information that's in the one you just shuffled. So there's 4 different versions of the permutation test, which are the single pass forward test, the multi-pass forward test, the single pass backwards test, and the multi-pass backwards test. So there's just 4 different ways that you can slice this test. The 4 versions of the test will give you different results when the predictors are strongly correlated, but if the predictors aren't strongly correlated, the 4 versions of the test usually give you pretty similar results. So what I always do as a rule is I run all 4 versions of the test and compare the results among them. And I generally look for similarities. before I make before I make a conclusion that such and such a predictor is important or unimportant, I make sure that at least 2 or 3 of the 4 versions of the test agree on that. So word of caution here, for all the results that I'm going to show throughout this course, when I use interpretation methods, whether it be the permutation test or something else, I'm applying all the interpretation methods to the testing set, which ensures that the results of the interpretation methods haven't been influenced by overfitting. But there's different schools of thought when it comes to this, and some people like applying interpretation methods to the training set instead. Because even though you might have overfit the training set is what the model truly learned from. So some people think if you want to truly know what a model has learned, you have to run the interpretation methods on the data used to train the model. Although in my experience, I usually get similar results whether I do it on the training or testing data. So the single pass forward test, I'm not going to read through the algorithm here in the interest of time and in the interest of probably not boring everyone by reading through a bunch of, I mean, essentially this is pseudocode. So I'll just walk you through the GIF on the right-hand side instead. So this GIF is showing you what the single pass forward test looks like. So each one of these columns is, this green thing is basically your predictor matrix. Each column is one predictor variable and each row is one example. And then the purple column is your labels, which you don't touch during the permutation test. So when the column is solid green, that means the predictor variable is clean, so it hasn't been permuted, it's in the correct order. And then when it turns into that weird diagonal brick thing, that means the values in that column have been shuffled or permuted. So basically what you do is you go through your data set once and you only permute one predictor at a time, and then you run that perturbed data through the model and you see what the new loss function is. And if the loss function decreases by a lot, that means the predictor you just permuted is important. Otherwise, the predictor you permuted is probably not important. And the kth most important predictor is the one that causes the kth highest loss, or the kth greatest increase in loss when you permute it. And you'll see that in the results that I'm going to show later on. So the GIF on this slide is showing you what the multi-pass forward test looks like. So in this case, I wonder if I can go back and start the GIF over. Yeah, I can. So at first you do the single pass forward test where you just go through and you shuffle one predictor at a time. But after you've done that, you figure out which of those predictors cause the greatest increase in loss or which of those predictors is the most important, and then you leave it permuted forever, which is when I put the do not touch sign over the predictor. That means it's permuted forever and you never bother unpermuting it. So you go through, you do the single pass test once, you find the most important predictor, leave it permuted forever. Then you find the second most important predictor, leave it permuted forever. Then you find the third most important predictor, leave it permuted forever. So the analogy I like to make is 99 bottles of beer on the wall, although Amy wouldn't let me put that in our BAMS paper. So that's the single pass and multi-pass forward test. The single pass and multi-pass backwards tests are similar, except that instead of starting with all predictors in the correct order, you start with all predictors being permuted, and then you successively depermute or clean up one predictor at a time. And on this slide here, I'm showing you your results from the COLAB notebook. So on this particular slide, I'm showing you the single pass forward test on the left and the multi-pass forward test on the right. And then the next slide, you'll see single pass backwards and multi-pass backwards test. The confidence intervals, or those orange error bars, those are showing you a 95% confidence interval for what the loss is after permuting that one predictor variable. And in this case, my loss function is negative AUC, or negative area under the ROC curve, just because the loss function in my code has to be something negatively oriented. So it has to be something where lower is better. But for area under the ROC curve, higher values are better. So I just multiplied area under the curve by -1 and use that as my loss function. But here I'm plotting positive area under the curve. So if you look at the results from all 4 versions of the permutation test, note also that we have 41 predictor variables for this problem of predicting strong thunderstorm rotation, but I'm only showing the top 20 in these plots just to make it less busy. So regardless of which version of the test you're looking at, whether it's single pass forward, multi-pass forward, or the backwards versions of those 2 things, the way I plot the data, the most important predictor is always at the top and the least important predictor is always at the bottom. So if you look at the figure for the single pass forward test, the most important predictor is maximum U wind inside the storm, and then there's minimum V wind inside the storm as the second most important, and then maximum V wind is the third most important. Note that minimum V wind, because V wind is the eastward component of the wind, when that's the minimum value is the largest negative value. So that's the strongest easterly, the minimum V wind is the strongest easterly wind, and the max, sorry, I'm mixing up my V and U. It's been a long day. The minimum V wind is the strongest northerly wind, and the maximum V wind is the strongest southerly wind, because I allow those values to be negative. So if you look at all 4 versions of the permutation test, you'll notice that they have a lot of things in common. So among the 7 most important predictive variables from the 4 different versions of the test, there's 4 variables in common among those 7. So one is maximum westerly wind, or the most positive U component inside the storm. Another is maximum southerly wind inside the storm. Another is maximum composite reflectivity inside the storm. And another one is the area of the storm, or the areal extent in square kilometers. So those are 4 things that appear to be important no matter how you slice the permutation test, no matter which version you use. So the last thing I'm going to cover here is saliency maps. You're going to see saliency maps again in lecture 5 on convolutional neural nets, but they're going to be a little bit different because they're going to be shown in image space. So for convolutional neural nets, we're going to be taking full 2-dimensional images of the storms and using those as our predictors. So when we plot saliency maps, they're going to be in that same gridded space. It's 32 by 32 grid cells. But in this case, we have only tabular data as predictors. We just have these 41 scalar values. So the saliency maps are a little bit weirder to visualize, but you can still get a saliency value for each one of the 41 predictors. So to tell you what's good about the different interpretation methods, the permutation test is great for determining which predictors are most important on average, because you're averaging over your entire data set, in this case the testing set. I apologize, I forgot to replace this triple X thing with the Microsoft math equation stuff. This is supposed to read X subscript J. I left these as a placeholder for myself and forgot to fill them all. So what the permutation test doesn't tell you, which is one of the disadvantages of it, it doesn't tell you the direction of the relationships. So for example, it can tell you that max composite reflectivity is a really important predictor, but it doesn't tell you what happens to the output, which is strong rotation probability, when you increase or decrease maximum composite reflectivity. So you don't know if the relationship is proportional or inversely proportional, for example. And also the permutation test, since it only gives you an average over the data set, it doesn't tell you which predictors are most important for a given example, and that can change, for example, by regime. So for example, one set of predictors could be important for supercells, whereas another set of predictors is important for mesoscale convective systems. So saliency, which some people also call sensitivity, is defined in this equation, and it answers both of those questions that the permutation test doesn't answer. So saliency is just a linear approximation to this derivative, di A di x. It's a linear approximation around the point x equals x naught. So A in the numerator is the activation of one neuron, which is typically an output neuron. In the CoLab notebooks we have here, we're only focusing on the output neuron. So A will be the probability of strong future rotation. It's the final output from the neural net. But you can do this for a hidden neuron as well, if you prefer to. And then x is one predictor variable, and x naught is the value of x, or the value of that predictor variable in a real example. So you create one saliency map for each example. So in plain English, saliency is a linear approximation to this derivative di A di x, and it's valid around the x value found in a real example. So saliency can be used for any model that does gradient descent. So this isn't something particular to neural networks. You can use it for linear and logistic regression. You can use it for any type of neural network. But for example, you can't use it for decision trees or forests because they don't have gradients. That's not the way they learn. Like I said, in the CoLab notebook, we're only looking at the activation of the output neuron. So our saliency maps, the ones I'm going to show you, quantify the sensitivity of strong rotation probability to each predictor, and I just call that P. So in other words, the saliency maps I'm showing you are answering the following question from the perspective of the neural network. We're asking the neural network, how would you change the storm, or how would you perturb the storm to increase or decrease the probability of the storm achieving strong rotation in the future? So shown here are the results from the CoLab notebook, where the on the x-axis you can see saliency, and it can be either positive or negative. So when saliency is positive, that means strong rotation probability increases with the value of that that predictor. And when saliency is negative, that means strong rotation probability decreases with that predictor variable. So the predictors with the largest positive saliency are the maximum westerly wind, the maximum southerly wind, and the area of the storm, which is nice because those are three of the predictor variables that I identified as showing up in the permutation test as being really important. So now we know that these three predictor variables are really important, and we also know the average saliency for these three predictor variables. So we know the direction of the relationship, which honestly wasn't very hard to determine if you have any meteorological intuition. Generally, the larger the background wind speed, the greater the probability is of your storm achieving strong rotation, and also the larger the area of the storm, the greater the probability is of it achieving strong rotation. And then the predictors with the largest negative saliency are the minimum westerly wind and the minimum southerly wind, which are the same thing as the maximum easterly wind and the maximum northerly wind. So again, this is saying if you make the wind stronger, if you have stronger easterly winds inside the storm, or stronger northerly winds inside the storm, or stronger westerly or stronger southerly, you increase the probability of the storm getting strong rotation in the future because you've increased the background wind speed. And this is the last slide. This just contains references for all the citations that showed up throughout the other slides, and then the link to the Colab notebook that we're going to go to now. But I'll stop and see if there's any questions first as I load up the Colab notebook. All right, the link for the Colab notebook is in the chat, but I'm just going to wait a minute to make sure that everyone can get to it. It's in the chat, and I also sent it in a group email at the beginning of the lecture. And I need some water, so I'll be back in 30 seconds.
While we're waiting for Ryan to get back, I had one other question, because this is lesson number 4. Next week we do convolutional networks. And then the next question is, what do we do after that? And so I'm going to post a list of potential topics that we thought about over here in the chat. And if you feel like it, you can already comment on it in the chat. So Ryan, while you were getting water, I was just telling people that I put a list of potential topics for lesson number 6, which didn't have a topic yet. In the chat, you can also suggest new things, or you can say, well, I really like number 1 or number 2 or whatever. And we can probably do 2 of those topics. But anyway, just feel free to take a look and put your comments in the chat or send us email. With that, I turn it back over to Ryan.
Thanks, I totally forgot to do that. All right, so once you've got the Colab notebook open, it's the same procedure as always. So you want to connect to a virtual runtime just by clicking this connect button at the top right. And then once you've got that done, you'll have to run any code cell marked required. And I tried to make those all the cells that are required are at the top, except there's this sneaky one down here near the bottom just before the permutation test where you have to read a pre-trained neural network. That's just to make sure that we all get the same results when we run our interpretation methods. So I'll get you to go to this cell here, which is called clone the Git repository, and you can just run through and run any code cell marked required. And again, you can do that by hitting the play button, but you can also hit Shift Enter or Control Enter. I think a few other keyboard combinations work, so whatever is easiest for you. So we're just going to read the input data, normalize the input data, binarize the input data, and I believe I fixed the code in this code cell pursuant to yes. So someone gave me a tip last week that this code was spitting out some printouts that didn't make sense, so I fixed that up. So this, as you go down the table of contents on the left-hand side, once you get past running all the boilerplate stuff that's marked required, I have this this section on fully connected neural networks, and again, the information is here the information in here is mostly redundant with the information in the slides. But if you prefer to read it again with slightly different wording, if that's the way you learn, I've kind of put slides, quote unquote, inside the Colab notebook that explain it in a slightly different way. So that may be useful for you. It may not be. The plots of the activation functions are created here. So both of these plots are exactly the ones that I showed in the slides. But if you're interested in how to create them and how to run activation functions outside of a neural network, which sometimes is a useful thing to do, we call that running the activation functions as a standalone instead of completely built into the neural network. You can see how to do that if you go to utils.py and then look for these two methods, plot basic activations and plot fancy activations. And then there's a section explaining dropout regularization, batch normalization, and then finally we get to our basic example. So I'll walk people through this basic example. This creates a very simple fully connected neural net, and then trains the very simple fully connected neural net, and then evaluates the neural net, and then that's followed by a hyperparameter tuning experiment, which I won't walk you through the details of that because you've already seen that in a couple lectures. So I'll show you how to create and train this basic neural net, and then I'll show you how to run the permutation test as well. So this cell with the text here explains the architecture of the neural net that we're about to create. So this is the list of hyperparameters. The dropout rate is 0.5 or 50% for all the hidden layers. The dropout rate is 0 for the output layer. So as I think I alluded to earlier, in my experience, if you use dropout on the final layer, which is the one that returns your predictions, you often get really bad predictions. So I never apply dropout to the final layer anymore. But I think some people still do. I don't think that's a universal practice. So again, your mileage may vary. The activation function for the hidden layers is Leaky Relu with a slope of 0.2, which is exactly the Leaky Relu plotted in this purple curve here. That just means it takes every negative value and multiplies it by 0.2. So it diminishes the magnitude of negative values by 80%. The activation function for the output layer is sigmoid because we're doing binary classification. There's no L1 regularization at all. And then there's L2 regularization with a strength or a weight of 0.001 for all layers. Convolutional layers was a typo because there's no convolutional layers in here. So what do you know, fixing typos on the fly. And then the other hyperparameters are all architectural, and they're shown in the table that's printed when you run this code cell. So if you click play, you'll run this code cell, and you'll get the same table we were just looking at. This top command here is just telling us the number of predictors that are in our training data, because that's required as an input argument for this method, which is called setup densenet, which again is in that utils.py file.
Ryan, there seems to be a question in the chat for you. Would you mind taking a quick look?
Oh,
sure. Very last comment in the chat. You can ignore everything else.
Okay. Did I comment that there was a utils error? Oh no, the error that happened in the last lecture, which someone pointed out, was that when I binarized the target variable, so I took the target variable and converted it from real values into just these binary categories being 0 or 1, and I did that by thresholding the variable, which is max future vorticity, at this value, which is 3.85 times 10 to the minus 3 inverse seconds. When I printed out the, I created these informative little print messages, and this last one, since it's printing binarized target values, should only be printing zeros and ones, and it was printing numbers with decimals last time. So someone pointed out that error to me, but it's since been fixed in all the notebooks. So I hope that answers your question. Okay, great, thank you. All right, so we're, this is kind of under the hood because the nitty-gritty code is all down in utils.py. But inside utils.py, I'm using the Keras library, or some people have heard of the TensorFlow library. So Keras is the high-level interface for TensorFlow. So all the programming that I do for neural nets is done in Keras, but then under the hood, Keras is calling code in TensorFlow, just to help everyone understand sort of the hierarchy between Keras and TensorFlow, because I know that's not always clear. So when you create a neural net inside Keras, you always get this model object, and if you you can just run the command model object.summary, and that's done inside this method inside setup densenet, which is why I don't need to do it again. But when you run model object.summary, you get this little table, this little flowchart type of thing telling you what your model looks like. So it gives you a list of all the layers inside the model and then the shapes of those layers. And the none thing here is it's a little bit annoying. I think it always confuses people at first. This is the batch size. So when you train a neural net inside Keras, the batch size is just the number of examples in each training batch, and that can be anything. So here it's represented by none. So if your batches were all 1,000 examples, this first dimension would always be 1,000. So for the input layer, the second dimension here is the number of predictor variables, which is 41, as we've gone over before. And then for all following layers, the second dimension is the number of features. And again, the features they're transformed versions of the 41 input variables. So these 41 variables are all raw weather variables, and then these 1,000 features are all transformed versions of the raw weather variables. So we have one dense layer or fully connected layer. The two terminologies are interchangeable. So we have a dense layer with 1,000 features, followed by leaky Relu activation, followed by dropout, followed by batch normalization. And then we have another dense layer. This one spits out 178 features, followed by leaky Relu, followed by dropout, followed by batch normalization. Then a third dense layer. This one has 32 features, followed by leaky Relu, dropout, batch normalization. A fourth dense layer, this one produces 6 features, followed by leaky Relu, dropout, batch normalization. So we have basically the same architecture repeated 4 times over, where it goes dense layer, activation, batch normalization, dropout, which in my opinion anyways should always be the order in which you apply those operations. It should always go, it should be your dense or convolutional layer, followed by activation, then dropout, then batch normalization. So after those 4 blocks, finally we have one more dense layer which only produces 1 feature, and this is the final outputs. This is the probability of strong rotation. And then we have our activation function, and this last activation function is a sigmoid. So it forces this one value to lie in the range of 0 to 1, so it can be interpreted as a probability. You may be wondering about the number of features that occur throughout the network. So we go from 1,000 down to 178, down to 32, down to 6, down to 1. That's just an exponential curve that goes from 1,000 down to 1 in 5 steps, which is why the numbers are so weirdly specific. I found that as a general rule, exponentially decreasing the number of features coming out of your layers works well, as in your network gives you good predictions, and it also doesn't take a really long time to train. If you don't decrease the number of feature values really quickly, then you get a huge number of parameters inside the neural net, and it takes a really long time to train. Even with this this aggressive decrease in the number of dense layer features, you'll see for the connections between the input and the first dense layer, or sorry, between the first dense layer and the second dense layer, there's 178,000 weights to learn there. If I had made this number 800 instead of 178, there would be a little over 800,000 weights to learn there. So if you don't really aggressively decrease the number of dense layer features quickly, then you often get a huge number of weights inside your neural net, and it takes a really long time to train, and also that can lead to overfitting. And another nice thing here is at the bottom you get the total number of parameters. Parameters means weights plus biases, and then the number of trainable parameters, because some of these are just constants. So this is the number of weights plus biases that you have to learn. So in that example Imme was showing with a little over 50,000 parameters, that seemed like a really high value after we've done linear and logistic regression and decision trees. But actually for most of the neural nets that I use in practice, I find that I usually have over 1 million of these parameters. Sometimes I have over 10 million of them. Okay. So this next code cell here is showing you how to train the dense net that we just created. And again, the details are kind of hidden away from you in this utils.py, but if you want to go inside utils.py and see what's under the hood, you're always welcome to. And I'm pretty sure, yes, I sent a link to the full GitHub repository last week, so you can find utils.py and go look inside there. So it takes some input arguments. And actually, before I start explaining that, I'm going to start running this code cell just because it takes a minute or two to fully go. And then you'll see what it looks like as you're training a Keras model, because you get these nice informative printouts. So the first input argument is the model object, so that contains the architecture and the loss function, all the information you need to know about the model before training it. So that's the basic DenseNet object that we just created. You need to specify the output directory because this model is going to be saved somewhere. You need to specify the number of epochs. The number of epochs is the number of times that we run through the training data while we're training the net. So 20 means that each training example is used 20 times to adjust the weights inside the neural net. To have this neural net fully converge, you probably need a little more than 20 epochs. I have the 100 commented out here, but just in the interest of time, I didn't want to try to train for 100 epochs on the fly while I'm talking to everyone. And then you need the predictors and targets for the training data and the predictors and targets for the validation data. So one thing I do here, you may be wondering why I'm sending validation data into the training method. I use this validation data for monitoring during training. So you'll notice that after every single epoch, you get this list of metrics, or this list of evaluation scores. So there's loss, accuracy, binary CSI, et cetera. And then after that, I've lost my horizontal scroll bar. Oh, there it is. So after all these scores, you get the exact same scores, but you get them on the validation data instead of the training data. And this is just it's a good diagnostic of figuring out whether or not your model is overfitting. So if you see that the metrics on the training data keep getting better and better, but the metrics on the validation data aren't getting any better, or maybe the metrics on the training data are getting better and better, but at the same time, the metrics on the validation data are getting worse, then that's usually a sign that you're overfitting and you want to stop training. There's some fancy things you can do inside Keras where you can, one of them is called early stopping, for example, where let's say you've set your model up and you've told it to train for 1,000 epochs, but you can put an early stopping callback in there, is what it's called, a callback or a callback object. So you can put this early stopping callback inside your model, and the early stopping callback can say, for example, if the validation loss hasn't decreased over the last 10 epochs, just stop training, whether or not you've gotten to 1,000 epochs. So you may only be 50 epochs into the 1,000, but if you find that validation loss hasn't improved over the last 10 epochs or over the last 30 epochs or 50 epochs or whatever threshold you want to set, then you can just stop training early, because it's a good sign that that if you continue training for the next 950 epochs, it's probably going to be a waste of your time, especially if you're on a supercomputer or a high-performance computing system where you have an allocation and you don't want to use up all your hours. Early stopping can be really valuable. So this is what it looks like when you train a neural net inside Keras. These are the sort of printouts that you get. And then after you've trained the neural net, you obviously want to evaluate it on separate data. So you've seen code similar to this for linear and logistic regression and also for decision trees. So this command up here, I'm calling utils.apply neural net, and here I'm applying the neural net to the training data. And this number of examples per batch, you can kind of ignore it. The whole idea is that I have something like 76,000 training examples. If I try applying the neural net to the 76,000 training examples at once, sometimes I run out of memory because there's not enough RAM on this virtual machine that I'm connected to. So instead, I make the predictions in batches of 1,024. And if you're wondering why it's a weird number like 1,024, it's just 2 to the power of 10. And like a computer scientist, I've started thinking in powers of 2 instead of powers of 10. So this command here creates the forecast probabilities for the training data, And then I compute the event frequency or climatology over the training data because I need that to plot the attributes diagram. And then utils.eval binary classification is just taking those probabilities that I just created and evaluating them and figuring out how good they are. And then I do the same thing for the validation data. So I create the forecast probabilities for the validation data, and then I evaluate those probabilities for the validation data. So if you just run this code cell, you'll see that the neural net runs really fast in real time. So despite the fact that it takes a while to train, that just went over 76,000 examples in, what, 2 seconds, 3 seconds? So it was really fast. So here you're seeing the ROC curve, performance diagram, and attributes diagram for the training data, and then ROC curve, performance diagram, and attributes diagram for the validation data. And I don't want to spend too much time doing a deep dive into this evaluation stuff, but if you look at the ROC curve for both the training and validation data, you'll see that the AUC is well above 0.9, which is usually considered the threshold for an excellent model. In the performance diagram, you can see that the maximum CSI is a little bit above 0.4, and it occurs around this 1-to-1 line where you have a frequency bias of 1. So that means you can get a completely unbiased model with nearly the highest CSI over all the probability thresholds. So that's always a nice thing to see. And then if you look at the attributes diagram, this reliability curve, which is the curve in red, is pretty close to the 1-to-1 line, although it's generally above the 1-to-1 line, which means that you have some under prediction or underconfidence here. So for example, when the forecast probability is 40%, the actual frequency of strong rotation is about 55%. When the forecast probability is 60%, the actual frequency is around 70%. So there's a little bit of under forecasting here. The next block, if you go through the table of contents, is on tuning hyperparameters. You've all seen code that does that before in previous lectures, so I don't want to go over that again. And then the next section is on the permutation importance test. So again, I've put some slides, quote unquote, inside the Colab notebook in case you want to see things worded a little bit differently than in the PowerPoint slides. You've always got sort of a different version here. So I talk about the single pass forward test, the multi-pass forward test, and then the 2 backwards versions of the test. Here is this is the other required code cell that might sneak up on you as you go through this notebook. You need to read in this pre-trained neural network, and the reason I do this is just to make sure that that you get the same results as me when you run the permutation test and when you create saliency maps. So the permutation test actually creates quite a while. Takes quite a while. If you're brave enough to run this code, it's not going to finish in the time we have because we only have a few more minutes. Oh yeah, it tells me the last execution took 1,290 seconds, so 21.5 minutes. So it takes a little while. But I'll walk you through setting up the permutation test. Also, you'll notice that because the permutation test is so computationally expensive, I haven't run the permutation test on all the examples in the training data. So what I've done, the training data I think is 27,000 examples. Instead of running it on all 27,000 examples, which would have taken hours, I randomly took 1,000 negative examples and 1,000 positive examples. So 1,000 storms that achieve strong rotation and 1,000 storms that don't achieve strong rotation. And I only ran the permutation test on those 2,000 storms, just to make it a little more computationally sustainable. So that's what all this code here is doing. It's just creating a smaller version of the testing set. And then I call utils.runForwardTest, which runs both the single pass and multi-pass versions of the forward permutation test. So the input arguments it takes are the predictor matrix, the predictor names. The reason it needs the names is just so that you can create nice plots. So these plots that I show you down here, this is why you need the predictor names. Otherwise, the predictor names would just be x1, x2, x3, and that's not very informative. And then you need the classes, so the true labels for all these 2,000 testing examples, and then obviously you need the model, which in this case is pre-trained model object. So that's the neural net that we just read in. So that's what you need to run the permutation test. And again, all the low-level details are in utils.py in this method called runForwardTest. And then to run the backwards version of the permutation test, the first 7 lines of code are all the same thing. in this case, for some reason, I only used 400 testing examples instead of 2,000. I probably, I don't think I meant that to be permanent, so I'll change that. And everything is basically the same. The input arguments to run backwards test are the same as the input arguments to run forward test. And again, all the real nitty-gritty details are inside utils.py. And then the last thing I'll show you is how to create saliency maps. So we have this method again inside utils.py. It's called getSaliency1Neuron. So you can do this if you want to play around and see what saliency maps look like for the for hidden neurons that are in the hidden layers of the neural net instead of just the output neuron. You can excuse me, you can change these input arguments and see what that looks like. So for example, you could look at the second last layer, which is a hidden layer, and you could look at, oh, I don't know, the fourth neuron inside that second last layer. And I actually have no idea what will come out of this. Oh, except it's complaining at me and telling me that's not a real thing. Okay, it's what I get for trying to write code on the fly. So the input arguments are the model object, which needs to be a model that's already trained, a neural net specifically that's already trained, and then the predictor matrix, the name of the layer that contains the neuron you care about, and then the indices of the neuron that you care about, because obviously each layer has multiple neurons, and then the ideal activations. This is used to create the loss function for saliency. So in this case, the maximum possible activation for this output neuron is 1. So I call ideal activation 1. But for a neuron that has a different activation function that's not the sigmoid activation function, you may want to set this ideal activation to be something different. You may want to set it higher to be like 10 or something. And then the last code cell is the one that plots the results. There's nothing super interesting in this code. I'm just creating a bar graph with the names of the predictor variables in there. So I hope this was helpful for anyone, and I'll stick around for probably 10 minutes to take questions. And also thank you everyone for voting on the topic for lecture 6. That's really helpful.
Any questions? Actually, let me stop the recording right here. And there's a question in the chat already, but let me stop the